So, welcome everybody. Happy New Year. Today's talk is by Gianmichele Di Matteo, who is in Karlsruhe, and he will talk about the local singularity analysis for the Ricci flow. Thanks for coming, and please go ahead.
Okay. Thank you very much for the nice invitation. I will talk about this local singularity analysis, which I introduced with my previous supervisor, Buzano. And thank you for the kind invitation. Let me give first an introduction to the Ricci flow and the problem. I recall you that in a Riemannian manifold, you can introduce a Riemann tensor, which I introduce here. And this gives a notion of curvature of two planes inside your manifold. And if you take a first sum of curvatures, so you take the trace of this tensor, you end up with a 0-2 tensor, that is the same as the metric. You take two vectors, it gives you a number, and this is called Ricci tensor. We know that this measures locally the distortion of the volume element with respect to the Euclidean one. And in harmonic coordinates, this is given by a negative multiple of the rough Laplacian of the metric, plus some lower order terms. It's not surprising for you probably that on the space forms, the Ricci is strictly positive, is a constant positive multiple of the metric on the round sphere, is 0 on the Euclidean space, and constantly negative on the hyperbolic space. If you take a further trace, so a further sum of curvatures, you end up with a scalar, which is called the scalar curvature. Hamilton in 1982 introduced the Ricci flow, which is an equation for a family of metric indicized by a parameter t, which we think of as a time. And these are all living on the same manifold M of dimension n. And we say that the family satisfies the Ricci flow if the derivative in time of the metric is minus twice the Ricci tensor of the metric at the time t. So in particular, in harmonic coordinates, the leading order is the rough Laplacian. And so you can expect that this is a weakly parabolic quasi-linear PDE. It's only weakly because we are fixing the coordinates in order to have this expression for the Ricci. As such, you can expect, and you do have, good results like short-time existence and smoothing. In particular, you can start the Ricci flow from really rough spaces, even some metric spaces in a suitable sense. And you have smoothing in the sense that you can have smooth bounds on the metric depending only on initial curvature bounds. But due to the nonlinear nature of the flow, you have singularities in a finite time. That is, that the flow cannot be extended smoothly past a certain finite time big T. And moreover, these are abundant in the sense that any initial metric with positive scalar curvature will give rise to such a singularity in finite time. Hamilton introduced this flow to show a remarkable theorem, which says that a simply connected free manifold emitting a metric with positive Ricci curvature is actually diffeomorphic to the sphere, to the tree sphere, and the Ricci flow is deforming continuously this metric towards a constant curvature 1. And later, as is well known, Perelman used this flow to prove the Poincaré conjecture. a key ingredient in a Perlman analysis is a deep understanding of these finite time singularities for Ricci flow in dimension 3. So let me tell you a bit about the general theory of singularities. So Hamilton proved that on a closed manifold, a Ricci flow is singular. So again, it cannot be extended smoothly past a finite time t, if and only if the curvature becomes unbounded at this finite time big T. And in that case, you even have this stronger inequality number 2. So the maximal curvature must be greater or equal than 1/8 times the remaining time to the singular time. Later, she extended this sort of result to Ricci flow with complete bounded curvature. What I mean is that the curvature is bounded on every compact subinterval of 0 big T. Of course, at the time t, it won't be bounded. Later, Hamilton distinguished between two cases. Type 1 flows, for which you can revert the inequality in 2. So every curvature must be bounded by some constant over the remaining time all along the flow and for every two plane in the manifold, or type 2 flows otherwise. Let me give you some examples. So let me clarify that the animations that will show, they are just animation and not numerical simulations. So in particular, they are not precise. And moreover, there is a key there is a key lack in this animation. That is, we are assuming that we can embed isometrically the entire family of the flow. This is not trivial in general. So this is the flow of a perfectly round sphere. So you can see that the sphere is shrinking homothetically. It's also getting more and more towards red. This is in this way I'm conceptualizing the concentration of the curvature, which in this case is uniform everywhere in the manifold. Then you have the example of a cylinder. Also in this case, you have curvature concentration everywhere. And let me just clarify that here the cross-section is assumed to be at least two-dimensional. This is a bit of a difference with respect to the mean curvature flow, because the cylinder S1 cross R is intrinsically flat, so it will not move under Ricci flow. A first non-trivial example, which is not shrinking homothetically, is the famous neck pinch singularity. So here you should imagine that you have a three sphere. Again, you need at least 3 dimensions to produce this example. And you with a metric such that it has this sort of shape. And you can arrange the curvature of the cross-sectional curvature here at the center of the neck to be positive enough, so much that it overcomes the two negative curvatures coming along this longitudinal direction. In such a way, their sum, so the Ricci tensor, will be positive at these points, and the flow will shrink this neck. And now, if the two sides are large enough, the neck will shrink before the two ends of this dumbbell shape shrink, and you will produce a singularity. The 3 examples we just shown you now are type 1 type 1 Ricci flows. If you want an example of a type 2 Ricci flow, you can rearrange a bit the dumbbell. So we consider the right end, the right tip, to be a bit smaller. If you make it too small, then the Ricci flow will just absorb the right hand, and you will end up with a round sphere eventually. If it is too big, you will end up with the neck pinch, which I've just shown. But in the middle, you might expect that you find a critical value for how big, for the size, say, of this right hand, in such a way that it will collapse exactly at the same time of the neck. In this case, you create this sort of spike, and you get a type 2 Ricci flow. So this, the fact that these animations are not numerical solution, it's also because this type 2 example, and actually every type 2 example, is expected to be non-generic among singular Ricci flows. So there's more or less no way of finding it numerically. So the two theorems by Hamilton and Ricci, which are given above, are a prototype of extension theorems. What I mean is that you're assuming some condition, for instance, boundedness of the curvature, in order to extend the flow. These were later generalized by Sesum and Ma and Chen, and they show that the flow can be extended as long as the Ricci curvature is bounded. Of course, this is a stronger theorem because the Ricci is an average of the actual curvatures. Rephrasing it, the Ricci tensor must blow up at every finite time singularity. And this was strengthened later by Wang, which proved that in this case, for singular Ricci flow, even the maximal Ricci curvature blows up at this type 1 rate. Of course, you don't have 1/8, you have a different constant. This time it's a bit harder. So it is natural to wonder whether you can extend the Ricci flow assuming only bounded scalar curvature. And the answer is yes, in low dimension. In dimension 2, because all the curvatures coincide. In dimension 3, by the Hamilton IV pinching estimate. And counterexamples are expected already in dimension 4 or in dimension 8. We'll try to give you some idea of why one can expect the dimension 8 critical for this question. But still no counterexamples have been produced yet. Is there any question, or can I move on? Okay, let me move and let me introduce you the singularity analysis. First, let me recall some definitions by Anders, Müller, and Topping, inspired by the theorems of Hamilton. They define a point in a singular, in a Ricci flow singular, if for every neighborhood of the point, the curvature is concentrating more and more on the neighbor as the time approaches the final time, big T. This set is denoted by sigma. Otherwise, a point is called regular. This means that there exists at least one neighborhood over which the curvature remains controlled from above in norm, say, up to the final time of the flow. Finally, if you have a singular point, you can pick up a space-time sequence pk-tk converging to p big T along which the curvature is blowing up. And we call it essential blow-up sequence for P big T. They show, oh, sorry, here there's a bad thing. As above, what I mean is type 1, which means, again, that the curvature is bounded by some constant over the remaining time. Sorry for this. They show that if you have a complete and type 1 Ricci flow, then a point is singular, that is, there exists an essential blow-up sequence for it, if and only if the curvature at the point P is blowing up at least at the type 1 rate. So in particular, you can pick this essential blow-up sequence with pk constantly equal to P, and any sequence of time will do. And the same holds for the Ricci tensor and the scalar curvature at the point. So this is a pretty nice characterization. Let me just remark the difference between this type 1 case and the open question on the bounded scalar curvature Ricci flows, which I've shown you above. So in particular, a bounded scalar curvature cannot be type 1. Exactly by the fourth point here. This theorem is based on a really non-trivial tangent flow analysis. If you want, I can spend a few words about it later. But I can tell you already that this is not valid without a global type 1 assumption. In particular, it's not valid not even if you use the brand new techniques introduced by Baumler in order to get singular tangent flows for general Ricci flow. Let me go on. Okay. First of all, let me set a bit on a notation. We call P naught T naught R the parabolic cylinder constructed in the following way. So you take the cross product between the ball of radius r centered at P naught and measured with respect to the metric at time T naught. And you cross it with the interval T naught minus R squared, T naught plus R squared. So of course, this is parabolic because here you, in space you have R, while in time you have R squared. And let me clarify that if this cylinder is crossing 0 or t, then you just take the intersection. Then we can give our definition finally. So we call a point a type 1 singular point if the supremum of the curvature on a parabolic cylinder of size comparable to the square root of the remaining time is blowing up exactly at the type 1 point along a maximizing sequence of times. And similarly, a point is type 2 if no matter how small you consider a cylinder relatively to the square root of the remaining time, then there will always be a sequence of times among which the curvature in this neighborhood is going to infinity. These are a bit technical definitions. I think it's more convenient to think of them in terms of essential blow-up sequences. So for a type 1 singular point, what we have is that we are asking for the existence of an essential blow-up sequence along which the curvature blows up exactly at the type 1 rate by dividing here, and which is type 1 close to the point P in the sense that it belongs to this cylinder. Similarly, by diagonal argument, if you want, upon this step 2, if you can consider, if you can pick an essential block sequence converging to p bit t type 2 fast, what I mean is that it's inside this cylinder where r is allowed to go to 0, and along which the curvature blows up at the type 2 rate. Let me remark that these cylinders are typically collapsing when you go to the singular time. So even though we call this singularity analysis local, this is actually a bit weaker than local. It's not yet a pointwise analysis. That would be nice, but it is a bit stronger than local. Oh yeah, you can give completely analogous definitions for the Ricci tensor. With these definitions, we managed to prove that for a bounded curvature Ricci flow, any singular point is of one of the two types just introduced. And the same, the completely analogous result for the Ricci singular set. So in particular, near every singular point, the curvature is blowing up at least at the type 1 rate. Notice that here we are not assuming the completeness of the flow. Also, we can prove that if you have a complete and bounded curvature Ricci flow, then any singular point is a Ricci singular point. So in particular, if you combine these two theorems, you have that near every singular point, the Ricci curvature is blowing up at least at the type 1 rate. And this generalizes, localize most of the results which I showed you above, all of the extension theorems. Let me give a short idea of the proof of theorem 2. We introduce a new regularity scale. This is given by the maximal radius small r, such that the curvature is bounded by r to the minus 2 on a parabolic cylinder or size r. Typically, regularity scales were used because once you are just inside a cylinder of size given by the regularity scale, then you have a completely smooth bounds on your flow. In our case, instead, we use them to prove this alternative characterization of the singular set by means of rate of divergence of the regularity scale. So we had that a point is step 1 if and only if the regularity scale to the minus 2 pt is blowing up at, exactly at the type 1 rate along a sequence of maximizing times. A point is step 2 if there exists a sequence along which this quantity is going to infinity at the type 2 rate. And a point is singular if and only if the regularity scale is infinitesimal, or rephrasing, you have this limit here. Once you prove this, we actually prove the stronger result that if a point is singular, then you even have the stronger property that the regularity scale to the minus 2 pt is greater or equal than 1 over the remaining time. And in particular, a singular point must be, by the characterization given above, of one of the two types which we introduced. For time reasons, I won't spend any further words on this proof, but I can tell you that it is rather simple. It sort of comes from the definitions. I want to spend a few more words on the proof of this Session type result. So by contradiction, we pick a singular point, which is not Ricci singular. By our characterization in terms of the regularity scales, we know that the Ricci regularity scale is bounded away from 0 by some constant delta, positive. Whereas the regularity scale, the Riemann regularity scale is infinitesimal along a sequence of times. The idea now is to argue inside a region of size delta in order to produce a global blow-up, adapting an idea of Hein and neighbor. How do we do it? We consider a minimizer Qi of the following functional. So you see here, if we were to minimize only the Riemann scale, we will get a sort of maximum of the curvature. Instead, since we want to argue inside the region of size delta, we penalize the distance from the boundary of the region. And we consider the minimizer inside the region where we have Ricci control. We set Ri to be the Riemann scale at this minimizing point, and we consider a sequence of rescaling given exactly by the factors Ri to the -2 and centered at Qi Ti. By the property which I told you before, these are defined definitely on the spacetime M cross -1, 1. Now, once you rescale, by definition, you have the new Riemann scale at Qi 0 is going to be equal to 1 for every I. And moreover, if you take a half the distance from the boundary of the minimizer Qi from the boundary of the rescaled region, this is going to infinity by this identity. You just need to rescale here, the minimizing property here. In particular, if we consider the ball or radius di, this is still contained inside this region because di is a half the distance of the minimizer Qi from the boundary. And for every point in this ball, again, by the minimizing property of Qi, you have our lower bound on the Riemann scale by a half. But I mean, this is just the minimizing property of Qi. But now, a lower bound on the Riemann scale implies an upper bound on the curvature. And this is happening on balls of radius di, so on larger and larger balls. This implies that you can extract a pointed smooth linear Ricci flow thanks to a refinement of the compactness theorem of Hamilton due to topping. This is well defined and complete on the wall slab M infinity cross -1/4, 1/4. Moreover, the limit verifies definitely the Riemann scale at the central limit point is equal to 1 because it's the limit of 1. The curvature is bounded everywhere by 4 by definition of the Riemann scale. And moreover, since we argued everything inside the region where the Ricci curvature was controlled, the rescale Ricci is infinitesimal because you multiply by this Ri squared. In particular, at the limit, the Ricci tensor is 0. But this means that the flow is actually coinciding with a static Ricci flat metric. In this way, we have reconducted the analysis to the same case treated by Session. So what we prove is we prove that we are in the rigidity case of the Bishop-Gromov inequality. In particular, the limit metric must be flat, and this is in contradiction with the Riemann scale at the central point equal to 1. Another theorem which I want to show you, because it will play a role later, is the following. So suppose that you have alpha and beta integrability exponents verifying this inequality, this identity, sorry. This is to ensure that this quantity, this mixed integral norm, is a scaling invariant quantity. So I'm taking the function to the power alpha, integrating in time with respect to the varying volume element, then to the power beta over alpha, and then integrating in time. So this theorem says that at a singular point, if you are close enough to the singular time, this scaling invariant quantity is bounded away from 0 and infinity. The way you should think of it is that despite this Riemann scale to the -2 is going to infinity, and the cylinder is collapsing, is collapsing geometrically, at least in the size, these two behaviors are sort of balancing each other out. And the same result also for the Ricci tensor in place of the Riemann tensor. It's not clear whether you can have a similar integral curvature concentration for the actual tensors. And in order to prove this theorem, we show that the regularity scale that we introduced is Lipschitz continuous in space and a half Hölder continuous in time. Let me give a short idea of the proof. So assume that you have the Lipschitz continuity violated at 2 points in the same time slice. Then in the orange region, which has size Riemann scale Pt, you have the curvature is bounded by Riemann scale to the -2 Pt, by definition of Riemann scale. If you set R to be this radius here, which is slightly smaller than the Riemann scale Pt, of course, this is bounded by R to the -2. And by definition of this radius, the parabolic cylinder centered at Qt and size R is contained in the orange region. Therefore, you have an upper bound on the curvature, even on the blue cylinder. And by definition of the Riemann scale centered at Qt this time, this must be strictly bigger than R. And this gives a contradiction to this contradicting inequality. Similarly, we assume that the Hölder continuity is violated at the same point P for 2 different times T and S, and we want to fit inside the orange cylinder a red cylinder over which we have curvature control. The way to do it is using a refinement of local distance distortion estimates due to Simon and topping. And you have some sort of constant coming from their theorem. And then we argue the same. The curvature bound on the orange region implies a bound on the red region, which implies a bound on the Riemann scale in this new central point PS, and this is contradicting the violation of the Hölder continuity. Once you prove these continuity properties, you can deduce a local Harnack inequality which essentially implies that the Riemann scale cannot oscillate too much quantitatively if you go just inside the cylinder, just a bit inside the cylinder. And in this way, we can prove the lower bound on the mixed integral norm thanks to the lower bound in this local Harnack inequality and Perelman non-collapsing theorem. And the other bound comes from this upper bound combined with the Bishop-Gromov inequality. Is there any question? Okay. Let me move to the Bandescar curvature flows case. Let me present the two theorems. So we assume that we have a closed Ricci flow, dimension strictly smaller than 8, with Bandescar curvature all along the flow. Then if for some alpha, the injectivity radius satisfies this bound 13, so it's controlled from below by some multiple of the maximal Ricci curvature to the minus a half, then the flow can be smoothly extended past the finite time t. Rephrasing it, such a Ricci flow is singular if and only if it collapses geometrically faster than the maximal Ricci curvature to the minus a half. And this is a really fast geometric collapsing. And the second result is a codimension A result, kind of. So we have a Bandescar curvature closed Ricci flow. We assume, this is a bit technical, that every point such that the Ricci scale to the minus 2 is sufficiently large is well behaved, in the sense that this Ricci scale to the minus 2 is uniformly comparable to the Ricci tensor at the point pt for some uniform constant delta. Then the singular set is empty in dimension smaller than 8 and has codimension 8 in a suitable sense in higher dimension. So let me give you two remarks here. So this inequality that the Ricci tensor is smaller or equal than the Ricci scale to the minus 2, this is always true by definition of the Ricci scale. So the important part is this one. In particular, the geometric picture is that we don't want the Ricci tensor to drop too fast from the maximal point somehow, at least near the singular point. So we want some sort of control of how fast the Ricci curvature might drop from the singular set. And this codimension 8, in a suitable sense, what I really mean is that we can control the rate of decay of volumes of the singular set. If you want, I can spend a few words more later about this. Idea of the proofs is that for Bandescar curvature Ricci flow, you can always control the Ricci tensor with the square root of the Riemann tensor. And this on a cylinder of scale, the Riemann scale at the central point pt. This is an idea of Bing Wang. Now, if we had an integral curvature concentration for the Ricci tensor, so similar to the one that I showed you above, this would imply a concentration of the Riemann curvature with halved exponent by this inequality. So this is a graphic of the integrability exponents verifying the condition which I showed you above. So if we add this integral curvature concentration, we could bound away from 0 the Riemann to the power n/4. On the other hand, there are integrability theorems by Bamler, Jung, and Simon, which says that the Riemann must be L infinity and almost L2 in space. That's why we can compare n/4 with 2, and we expect an 8. I will now try to explain this in more detail, but let me just state now that in fact we cannot expect this integral curvature concentration. At least it's definitely not trivial how to prove it. And so what we do is we try to deduce a similar inequality at the level of the regularity scales. So the Ricci regularity scale and the Riemann regularity scale. And this is equivalent to prove this inequality on a cylinder of size the Ricci scale, PT. So under the injectivity radius bound, or for the well-behaved points, as in our theorem 7, we can exactly show the analogous comparison, which I will denote in purple, between the Ricci scale and the Riemann scale. Is this one, as long as we have bounded curvature. Then we use our theorem, our Sesson type theorem, to pick up a well-behaved essential blob sequence, PITI. Then we want to use the integrability result, which I will denote in red, proved by Bamler. This time, this says almost the L2 norm of the Riemann scale to the -2, rather than the Riemann tensor. So these are stronger result by Bamler. On a suitable sequence of balls, this is infinitesimal. While on the other hand, we can control away from 0 the L alpha norm of the Ricci scale to the -2 on the same balls if the integrability exponent alpha is strictly greater than n/2. And we will denote this in orange. Altogether, we arrive to an inequality of the following form. So here we can bound the Ricci scale to -2 alpha on a ball of size Ricci scale away from 0 by our integral concentration. And here we assume alpha greater than n/2 for it. Then we use the comparison in purple to bound this from above by the Riemann to the power -alpha. Notice that this is on the entire ball of size Ricci scale. And finally, we can bound this from above by the radius of the ball to the power n-4 plus 2 epsilon by the integrability result of Bamler, if we assume alpha strictly smaller than 4. In particular, we are assuming n smaller than 8 in order to do this chain of inequality. And then you can just let I go to infinity and the right-hand side goes to 0 and you get a contradiction. So the contradiction is that you cannot pick up an essential blob sequence in dimension smaller than 8. So the flow must be irregular. Now, the codimension 8 result still comes from the comparison and the integrability result. And the injectivity radius bound is really similar to this 14 inequality. Finally, let me tell you about the future research and open question. In an upcoming paper with Reto, we prove conjugate e-kernel bounds, which are global and depend only on whether the base point is a regular, a type 1, and a type 2 point. So we can actually extend the bound on the conjugate kernel outside these cylinders of definition. It's natural to ask whether one can prove in general that the curvature at the point P should blow up at least at the type 1 rate. This is still a rather easy but open question. Can one rule out oscillation of the Riemann curvature between type 1 and type 2 rates? Also, this I like this question, is rather natural but still open. What we can show is that for a type 2 singular point, the only possible type 1 times for its regularity scale must converge to the final time exponentially. So in some sense, they cannot be too much dense inside the time interval, but still they might be present. Finally, can one prove the well-behavedness of the singular point under bounded scalar curvature without assuming any further technical assumption, like the injectivity radius bound? This concludes my talk. Thank you for your attention.
Thank you very much. Okay.